everyone. Welcome to 53rd Q-Chem webinar. I'm Kuan Yu Liu, a staff scientist here at Q-Chem. It's my pleasure today to introduce our speaker, Dr. Salim Sami. He'll be talking to us about automated parametrization of QM-based force fields using Q-Chem. Dr. Sami received his master's degree in theoretical chemistry and computational modeling scholarship with honors in 2016. Then he obtained his PhD degree under supervision of Dr. Remco Haverneth and Ria Brewer, focusing on prediction of dielectric properties of organic materials for photovoltaic applications. Later on, he joined Dr. Shirin Faraji's group at University of Groningen to work on QForce to excited states and its interface with Q-Chem. Since 2021, he has been working with Dr. Siewert Jan Merink on the reactive Martini force field and extension of QForce to force models like the Martini force field. Without further ado, it's yours. So,
thank you very much, Kuan Yu. Can you hear me well and see my screen well?
Yes.
Great. Okay. Hello, everyone. First of all, thanks to the Q-Chem team for organizing these nice webinars and also inviting me to present my work here. Today, I will talk about QForce, a tool that we were developing, and it has the goal of parameterizing molecular dynamics force fields based on quantum mechanical calculations in an automated manner and its combination with Q-Chem. So in computational chemistry, we're often faced with the dilemma between reaching long timescales and large length scales versus reaching high accuracy. The methods that can describe the intricate nature of electrons are often too expensive to, computationally expensive to simulate systems of biological relevance. So the tool I want to present today aims to increase the accuracy of these molecular dynamic simulations and do this without increasing the costs associated with these simulations themselves. And this is done by parameterizing the force fields that determine the interaction in these molecular dynamic simulations based on DFT calculations. Let's take a step back here and talk about force fields. So these force fields are what determines the interactions of a molecule within itself and also with other molecules. We have a variety of potentials here, starting with bonded potentials between two atoms and angle potentials between 3 atoms. And then we have flexible dihedrals. These are dihedrals that have multiple minima. So dihedrals that can freely rotate, as you can see here. Another type of dihedral are rigid dihedrals, and these have a single minimum, such as a conjugated ring. And we will get back to the difference of these two dihedrals later. And to model the non-bonded interactions, we have the Lennard-Jones term to account for the repulsion and for the dispersion interactions. And for electrostatic interactions, we make use of the Coulomb interactions. And this is a large, all this results in a large number of parameters that are needed to describe the complete molecular space. If one has to determine these parameters for each molecule, then we have to solve a virtually infinite size problem. And the solution to this was these general purpose force fields and their use of atom types. There are some very well-known examples of this. Probably you have heard of some of them. And what these force fields do is that they determine the atom type of an atom based on its chemical environment. So here we can say that this is an alkyl carbon, this is a carboxyl carbon, and this is an ether carbon. And whenever these atom types are identified again in a different molecule, then we simply use these atom types once again. And this makes this virtually infinite size problem into a manageable size. We end up with about 100 to 200 different atom types. And of course, all the combinations of these still result in more than 1,000 empirical parameters. And to solve this problem, over time, many automated topology builders have appeared that allows for a given molecule to give the force field for any of these general purpose force fields. For example, there's ATB for Gromos force fields, LIG-PAR-GEN for OPLS force fields, CHARM-GUI for CHARM, and Antechamber for Amber force fields. And these force fields work very well for either small systems or systems where the molecule resembles to the original molecules that were used to parameterize these force fields. As soon as we start encountering large and complex systems where we have chemical environments that were not present in the initial parameterization of these force fields, then we start encountering problems that the atom types no longer match. The existing atom types no longer match the molecule. And when this happens, we are often left to do a lot of manual labor. For example, QM dihedral scans match these potentials. And whenever there's a lot of manual labor involved, this often tends to be very time consuming and also error prone. So this is the first motivation for QM-based force field automation. That is systematic and transparent derivation of these force field parameters. And consequently, we will end up with significantly fewer, if any, empirical parameters. And assuming that we use the same functional form for the force field, after the initial parameterization, we can run MD simulations at the same computational cost, but with increased accuracy. And last but not least, we often use structures or morphologies or snapshots from molecular dynamic simulations for further QM calculations. For example, here you see a donor-acceptor interface of an organic photovoltaic material generated through molecular dynamic simulations. And then further QM calculations can be done at these interfaces to determine energy levels and so on. And when this is the case, it is very beneficial that the force field that was used to generate these structures matches the one that will later be used to perform the QM calculations. That agreement tends to be quite important. And with this, I move to the QForce force field. And for the previously mentioned reasons, that is, we have chosen to use a standard functional form. So you can see that for rigid terms, these are bonds, angles, and rigid dihedrals, we use a simple harmonic potential. For flexible dihedrals, we have a periodic potential. This one specifically is called the Reichert-Bellemans function. For electrostatic interactions, again, we have the Coulomb potential. And for dispersion and repulsion interactions, we use the Lennard-Jones potential. And as I mentioned, this standard functional form allows to run the MD simulations with no increased computational cost. And also, an additional benefit is that these can still be run on highly optimized MD software, such as GROMACS, Amber, or OpenMM. And an additional consideration we had is that these Lennard-Jones parameters that we use in this force field are inherited from a parent's force field. This can be a transferable force field, or any other force field. And this is for increased compatibility with the existing force fields in that force field library. And we will get back to this more in the results. Now, I will walk you through the different steps of the parameterization within QForce, starting from here all the way top and slowly walking our way down to the final result, that is the force field. To begin with, we need Lennard-Jones parameters, and these Lennard-Jones parameters, as I mentioned, are inherited from a parent force field. And in the case of OPLS and GROMOS, these are automatically detected, so no action needs to be taken. So the user simply has to input a coordinate file that can be one of these many different coordinate types. And these coordinates are then used first to perform a QM geometry optimization. And the optimized geometry is then used to determine QM-based atomic charges, and also to determine the QM Hessian matrix and the Weiberg bond orders. And for this, you can choose your selection of QM software. And in this talk, we will focus on Q-Chem, the compatibility of QForce with Q-Chem and how these can be used together. And all the necessary input, QM input necessary, is created automatically. We have this default method, but of course, the user is free to choose any other method to suit their needs. And for determining the charges, we use the CM5 charge model. And we scale these with a factor of 1.2. And this is for accounting for the condensed phase polarization. However, alternatives are available in Q-Chem, of course, and any of these can be used in combination with QForce. At the next step, we identify the topology of the molecule, for example, the rings and connectivity, based on the Weiberg bond orders. And this topology is then used to identify the force field terms that are present in the molecule, and also the equivalent atoms and, again, force field terms that are present. So think of symmetry here. And this helps reduce the number of fitting parameters in the procedure. And at this stage, the procedure is split into two. We have the rigid terms. So this is bonds, angles, and rigid dihedrals, and also flexible dihedral terms. Now, just to remind you the difference between these two, the rigid term has a single minimum, and it can be modeled by a harmonic potential. So a QM Hessian contains enough information to deal with these rigid dihedrals. On the other hand, flexible dihedrals have multiple minima, and the Hessian only contains information about one of these minima. So we will have to deal with these separately. But all the rigid terms are then used to do a Hessian fitting, where the MM Hessian is fitted to the QM Hessian by a least squares method. So we minimize this function. And consequently, we obtain the rigid force field parameters. And QForce at this stage automatically provides this plot where you can see the correspondence of the vibrational frequencies between the QM method and the QForce method. This will be provided automatically at every run. And for the flexible dihedral terms, this step was identified as the bottleneck computationally of the procedure. As you can imagine, the size of the molecules grow. It is quite unfeasible to scan tens or hundreds of dihedrals considering the whole molecule. This quickly becomes very difficult computationally. So to get around this problem, we have implemented a fragmentation procedure where we automatically identify and create chemically meaningful fragments. And here you can see an example of this fragment creation. So let us assume that we have this molecule and we are interested specifically in this dihedral. What happens is that automatically the first three neighbors of the dihedral is automatically included in the fragment. And for each next neighbor, we then make a decision based on a set of rules whether that atom should be included in the fragment or not. So here you see that there's a conjugated end in ring carbon-carbon bond. So this is not a bond that we want to break. So then this atom is included into the fragment. And then the next bond is a carbon-carbon single bond, which can easily be broken. So the bond is broken here. Similarly, on this side, there is no reason not to break this bond. And finally, we end up with this fragment, and this molecule is then a dihedral scan is performed on this molecule. And since we can encounter the same fragment on multiple different molecules, we have implemented a database to add any fragment encountered, so that when we see them again in a different molecule, we would not need to perform a duplicate calculations, and these will be automatically identified. All right, yes. And the last step of the procedure is the dihedral fitting. So what we start with here is this profile. So in blue, you see the QM profile, and in orange, you see the MM profile. And the difference, and this is before the dihedral fitting, and the difference between these two profiles are fitted to the periodic Reichert-Bellemans function that I was mentioning earlier. And consequently, we end up with such a good agreement between the two profiles. And just like with the Hessian fitting, also for each dihedral that is present in the molecule, such a plot is provided automatically at the end of the run, so that the user can decide if the fitting has gone successfully or if further action is necessary. And at the end of all this, we obtain the QForce force field. This is provided in the GROMACS format. So nowadays, this can easily be converted to any other format that you might be interested in, such as Amber or OpenMM. And as I mentioned, the Hessian and dihedral fitting validation is also provided in the folder. So speaking of validation, we also wanted to validate our procedure on a set of 16 small molecules. And what we have done is we created force fields for these 16 molecules with using the ATB for GROMOS, LIGPARGEN for OPLS, and we have also created a QForce force field. And for each of these force fields, we have computed vibrational frequencies and the overlap between QM and MM vibrational modes, the dihedral profiles, and thermodynamic properties. And I will walk you through these one by one now. So here you can see the QM versus MM vibrational frequencies. The first one is GROMOS, and then OPLS, and then in green we have the QForce results. And as you can see, for these two transferable force fields, the mean absolute error is significantly larger compared to the QForce force field, where you can see a very good agreement between the QM and MM vibrational frequencies. Here, the red line corresponds to a perfect agreement. Also, interestingly, for GROMOS, you can see here that between 500 and 1,000 wave numbers, you can see a consistent underestimation of the vibrational frequencies. And in fact, these vibrational frequencies correspond to the out-of-plane bending modes of conjugated rings. And this has the consequence that you can see here. The GROMOS-based tetracene is unrealistically floppy. And here you can see the behavior of QForce tetracene, which is significantly more rigid. And this difference has significant consequences, of course, on the pi-pi stacking of this molecule. So the small difference that you saw in the previous plot can have significant consequences for the properties that you're interested in. And aside from vibrational frequencies, also the vibrational modes that correspond to those frequencies are very important. And we look at this by means of overlap between the QM and MM vibrational modes. So 1 means a perfect overlap and 0 means no overlap. And you can see this for the 3 force fields. And for these small molecules, you can see that all 3 force fields perform relatively well. The QForce one has a higher mean overlap compared to the other 2 force fields, especially the Gromos one. All right, and then we look next at the flexible dihedral profiles corresponding to those same 16 molecules. And here with dots, you can see the QM scan data points, and QForce ones are the lines. And you can see that there's a good correspondence between the two. For each dihedral, the R squared is larger than 0.99, sorry. But of course, this is a profile corresponding to the relaxed dihedral fitting. It is also interesting if the same behavior is observed during the MD simulations. And to investigate this, we looked at the dihedral distributions of these dihedrals in the condensed phase and performed the inverse Boltzmann analysis to obtain the energy profile back. And you can see, well, first you can see that the highest energy barriers are not visited during the MD simulation, so we cannot show those. But for the rest, you can see that there's a very good correspondency between the two profiles. And finally, now that we have our force fields, we can look at the thermodynamic properties and compare them with experimental results. And the thermodynamic properties are dominated by non-bonded interactions, so Lennard-Jones and Coulomb terms in the force field. And to look at this in more detail, we have created 2 Q-force force fields, both of them using Gromos-Lennard-Jones interactions. And in one case, we have also used the same atomic charges that were used in the Gromos force field. And in the other case, we have used the scaled CM5 charges obtained from the QM calculations with Q-Chem. And here you can see the results. The mean absolute error with respect to the experiment is presented above for the density and below for the enthalpy of vaporization. And all these values are relatively low, but you can see that the Gromos force field and the Q-force force field with Gromos atomic charges perform very similar to each other, and this is in line with our expectation that if we use the same non-bonded interactions, we end up with very similar thermodynamic properties. However, when we switch the CM5 atomic charge, when we switch to CM5 atomic charges, we see that the mean absolute error decreases compared to Gromos for both of these thermodynamic properties. And this is a good motivation for having the default CM5 atomic charges in our QForce procedure. Now, small test systems are important to do, but of course, later on, we want to work on large systems. And this was a test of how QForce perform in a relatively large system. So this ITIC molecule consists of almost 200 atoms. It is relevant in the field of organic photovoltaics as a high efficiency material. And what we looked at here is the potential energies from QM and MM calculations and compare these energies. So what we did was we created, again, 3 force fields for this molecule, one with Gromos, one with OPLS. We created 4 force fields, 1 Gromos, 1 OPLS, 1 Q-force with Gromos Lennard-Jones parameters, and 1 Q-force with OPLS Lennard-Jones parameters. And for charges, in both cases, CM5 charges were used for the QForce force fields. And with each of these 4 force fields, we have taken 200 snapshots during an MD simulation. And at each of these snapshots, we have performed a single point QM calculation. And then we compare QM versus MM relative energies. And this is what you see here. So in blue, we have the Gromos values, in orange, the OPLS values, in green, the Gromos-based QForce, and in gray, OPLS-based QForce. And the red line you see in between, again, indicates the perfect agreement between the two. And you see here that the transferable force fields perform significantly worse compared to the QForce-based force fields, where you can see a very good agreement between the QM and MM energies. And this you can also see in the mean absolute errors that goes significantly lower in the case of QForce force fields. We can also look at the optimized structures for each of these force fields. So here in red, the QM optimized structure is shown, and in 3 other colors, the 3 different force fields are shown. And you can see again for the transferable force fields that the agreement between the optimized QM optimized and MM optimized structure is not so well. More specifically, the planar backbone of the molecule is broken and is no longer planar. And this is also reflected in the root mean square deviation between the QM and the MM structures that is significantly higher for both of these force fields. However, if we look at the QForce force field, there's almost perfect alignment of the QM and QForce geometries, which results in a very small RMSD value. One final thing we can look at to compare the relative performance of these force fields is the QM energies. And what we show here is the QM energy for the optimized geometry is set to 0. And here you can see the relative energies of all the snapshots that were taken. Now, considering the virial theorem, the average expected energy of this molecule is 683 kilojoules per mole, and this is based on the degrees of freedom and the temperature. You can see that the average energy of QForce is very similar to this expected value, whereas in the case of transferable force fields, you can see that it is off by hundreds of kilojoules. This has significant consequences. It means that the geometries that are visited in these simulations do not correspond at all to the ones one would get from a QM-based simulation, because they are very high in energy and they would almost never be visited. All right, and aside from this, we have also used the QForce procedure on several other systems, and we are interested in treating these large systems. So here you can see its application on these donor acceptor photovoltaic interfaces. And as I mentioned before, QM calculations are performed at these interfaces to deduce the energy levels of these molecules. Another application is the organic thermoelectrics, and here we do crystal structure determination based on simulated X-ray diffraction patterns. And finally, we have also investigated the dielectric properties of molecules using even the polarizable version of these force fields. And at this stage, I will move to my terminal to show you how you can use QForce in combination with Q-Chem. All right, hopefully you can still see my screen. So what we have here is first of all, a coordinate file in XYZ format for the propane molecule. And we have a config file, and these are where the settings for QForce go. And the only setting we need at this point is we want to specify that as a QM software, we want to use Q-Chem. And in this folder, I have the necessary QM output files because I do not want to run them right now. And the first step in the procedure is to get the QM input files by simply providing the, first of all, we do need to install QForce in this system. And this is something very simple. You can, in any system that has a Python 3.6 or above, you can simply pip install QForce, and this will work very quickly. There we go. We already have QForce now. And now we can run the first step of the procedure, which is to obtain QM input files. And this is now provided to us in this directory. So here you can see, sorry, a small mistake. I forgot to supply the config file. All right, there we go. Now we can open it again. So here you can see the QM input file. And we have the settings, the Q-Chem settings for the geometry optimization here. And after the geometry optimization is done, we do a frequency calculation. And we also ask for the NBO analysis, so we can order the we can obtain the Weiberg bond orders. And at this stage, I will simply copy paste the output of these QM calculations to the same directory, so that we don't have to run them. Yep. All right. Now that we have the output files, we simply have to do the same thing again, supplying the config file. And with the Hessian and bond order information, as I have mentioned earlier, now we can compute the Hessian and determine the flexible dihedrals in the system. So the propane molecule has two flexible dihedrals, but both of them are identical, and this is already identified, and it says that we have a single unique flexible dihedral, and QForce had created the Q-Chem input files in this directory for that flexible dihedral, and this you can see here. This is our molecule. These are the Q-Chem settings, and here you can see the relaxed scan that we asked Q-Chem to do. All right, and again, I will now copy paste the output of this calculation to that directory. Yes. Now that we should have all the QM calculations needed for determining the force field of this molecule, we can simply do the same thing one last time. And all of this, of course, can be combined very easily into a bash script. And here we are performing the dihedral scans, fitting the difference between the QM and Hessians to each other. We do this in a few iterations. This is not so relevant here, but for more complex molecules, when the dihedral profiles are coupled, having such iterations make the procedure yield more accurate results. All right, now we should have our force field. We go into the directory, and we can see what kind of files have been generated. So the first thing to look at is the force field file, of course, and this is given here. Let's look at this. So this is a Gromos file type for the force field. You can see the atom types and the non-bonded interactions here, and the atomic charges are provided here, the bond terms, angle terms, flexible dihedrals, and the 1,4 pair statements. So this is, and since we already have the topology and the coordinate file, this is already ready to be used for MD simulations. And as I have mentioned earlier, the plots corresponding to the Hessian fitting QM versus QForce is provided here in this PDF file. and the same is true in the fragment subdirectory for the scan dihedral. And yes, this is it. It is quite simple to both install QForce and use it. And I hope I managed to demonstrate this. Now I will go back to my slides. All right, coming to towards the end of the talk, there are two things that are still a work in progress. And first of all is the implementation of QForce for generating excited state force fields. So this technically already works, but we are, as part of my short postdoc with Shirin Faraji, we were working on determining the ideal parameters for to use to generate excited state force fields in combination with Q-Chem, and this is close to being finalized. And another thing I'm working on is related to my new postdoc position, and this is in the group of Siewert Jan Maring, who is the developer of the coarse grain Martini model. And not surprisingly, I am here interested in extending QForce to cover coarse grain force fields as well. And to conclude, first of all, both the code and the necessary documentation is available in GitHub, and you can find this here. And the paper is currently under revision, and hopefully the result will be available to the community soon. And I hope to have shown you today that the QForce procedure can be used for accurate and systematic derivation of QM-based force fields. And the fragmentation procedure allowed tackling large systems with ease. So very large systems are within the reach of QForce. And finally, I hope to have shown you that it can be used quite easily in combination with Q-Chem. And finally, I would like to acknowledge my collaborators, Maximilian Menger, who was helping me in this project, and my old and current supervisors, Shirin Faraji, Ria Brewer, Remco Havenit, and Siewert Jan Maring. And thank you very much for your attention, and I would be happy to answer any questions.
Thank you, Selim. It's a very interesting and informative talk. We already have a couple questions. First one, is the computational cost of the QM part or is it the bottleneck for the generation of QForce?
It is definitely the bottleneck, because the QForce procedure itself takes almost no time compared to the QM calculations. But as I have shown with the fragmentation procedure, the system that we studied, the ITIC molecule with up to 200 atoms, was still quite feasible, and it was done, I think, under less than 5 days of computational time in a single node. So I would argue that even larger systems are within reach. And if one is interested in very large systems, the QM calculations instead of DFT, we can use semi-empirical methods such as DFTB. And I think it would be possible to treat much larger systems with that.
Thank you. So our next one is, can QForce deal with a Q-Charm format?
So the input can be provided in the coordinate file can be provided in many different formats, but the output is currently only given in GROMACS format. But there are many tools in the community that can convert this from the GROMACS format to the Charm format. So I think that should not be a problem, but it is not available within QForce to directly give a Charm basically Charm format is not given. But if you mean Charm force field, then that is not a problem.
Thank you. One, so you showed that the intermolecular interactions can be reproduced well in QForce. What about the intermolecular interactions?
Yeah. So this is what we try to demonstrate with the thermodynamic properties. So that was the only study we did with regards to the intermolecular interactions, and indeed the thermodynamic properties are mostly determined by these intermolecular interactions. So we are confident that they are also in order.
Thank you. Question: is there a reason you chose the 1.2 scaling factor for CM5 charges?
Yes, this is a value available in the literature. So there's a study. Sadly, I don't remember the name of the authors, but they have tested different scaling factors to determine which one results in the best agreement with respect to thermodynamic properties for a variety of systems, including aqueous systems and pristine systems. And this value was determined to be the best balance one can decide. And the reason to have a scaling at all, and that is because the QM calculations are performed in gas phase, and the AMD simulations are done often in condensed phase, and the atomic charges are constant throughout the simulation, so they cannot be polarized in the condensed phase. And this is what we are trying to account for by scaling these charges.
Thank you. So next question: how does QForce perform in reproducing some dynamic properties like the viscosity or diffusion coefficients?
I have to admit that we have not tested either viscosity or diffusion coefficient. But again, I expect these to be closely correlated with the non-bonded interactions. So definitely more tests can be done and should be done. But since we inherit the non-bonded parameters from transferable force field, which has been validated over long periods of time, and we use a quite standard charge method, I expect that them to be in good order. But definitely more tests can be done in regards to this.
Thank you. Okay, our next question is related to dihedral fitting. Do you consider the 1 to 4 scaling factors, and what value do you use?
Yes, so for 1/4 scaling factors, we consider the default of the parent force field. So for example, if we're using OPLS force field for the Lennard-Jones interactions, then we use the scaling factors that correspond to the OPLS force field. If we're using Gromos for Lennard-Jones interactions, then we consider ones corresponding to those. But yes, they're always present.
Thanks. Next one, how does the change in QM level theory affect the results?
This is something that we have not checked extensively, but that we have checked this a little bit, at least between different DFT functionals, and the difference is not very large. It is well known that the hybrid functionals overestimate the Hessian. So what is commonly done is that a scaling factor is used to reduce the Hessian terms when using hybrid functionals, and this also can be provided to QForce. So if you use a hybrid functional, you can also supply the scaling coefficient that you want to use, and those values are available in the literature.
Thanks. So next question, how do you make sure that the new charges will be compatible with various force fields, as force field uses slightly different schemes to derive these?
Yeah, I think for optimal compatibility, one should stick with the default charge method of that force field. For example, if you're using a GUF force field, you can ask Q-Chem to provide you resp charges, and you can use these resp charges in combination with QForce, so that you ensure that you have the best compatibility you can have. But in this case, we have also shown that in some cases, using CM5 scale charges can in fact be better than the ones used by ATB Gromos force field, for example. But generally, it is a good idea to stick with the default charge method of that force field, and these are often available in Q-Chem.
Thank you. I think there is a follow-up question for this one. So all the work are done in gas phase, and how's the transferability for the result to like condensed phase?
Sorry, I didn't fully get that.
So so all this is done in gas phase, right? While most force field are parameterized to work in condensed phase. And are you sure you're not biasing things in a way that pass your benchmarks, but wouldn't really be transferable with standard biological force fields?
Right. So not everything we have done was in gas phase. So the computation of the thermodynamic properties were, of course, done in the condensed phase, and they do seem to be working well still. And another option that we're investigating right now, and one can already choose an extra keyword to do this, and this is you can perform the QForce procedure in an implicit solvent. So the whole parameterization can be done using an implicit solvent, and this can resemble more the condensed phase simulations that you will later be doing. And we are now investigating how this affects everything, and should this be the new default behavior of QForce.
Thank you. Next question. Could the QM calculation be performed with implicit solvation? Have you experimented with it?
Yeah, I think this is in line with my previous answer. We are currently experimenting with this, but yes, it can be done. So you can supply a keyword to QForce to create the input files for Q-Chem using an implicit solvent. But we are testing this further currently.
Thank you. Next question. So if we generate QForce parameters for aniline dipeptide, do you expect it to reproduce its sorry, I have a hard time to pronounce this, but it's a Ramachandran plot at QM level?
Yeah, so coupled dihedrals are also something we're still working on. I cannot answer, of course, right away whether it would work or not, but to make sure that it works, we're also working to implement these 2D correlated dihedral profiles, often called CMAP. So with the use of these CMAP potentials, definitely we can reproduce those plots that you were mentioning. But at this stage, well, one has to try and see, I think.
Thank you. Okay. So there are a lot of questions. Let's try to find if I miss anyone. So there is a question asking, is there a reason that you prefer Q-Chem over other available sorry, yeah, that's a question I wonder. That's
okay. So QForce can be used in combination with various QM software. But in this webinar, I have, since it's a Q-Chem webinar, I have talked about its combination with Q-Chem.
Thank you. Thank you again, Celine, for this very interesting talk.
Yeah, thank you very much for having me. It was a quite real pleasure to give this talk here.
And if you have questions later, you may post a question in the forum post. I already created one. It's a webinar 53. Can post your question here or contact me. And I also want to thank all the attendees for listening. And this is our webinar.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation and see you at the next webinar.